Okay, so today, like I said, we're going to talk about, let me make sure I'm sharing my screen. I'm sure I'm not. Hold on. Okay, so we're talking about integrated rate laws and half-life. So what we did in the last couple days and what your warm-up was about was differential rate law. Okay, and just to kind of go over what we've done, where we are, and what we're going to do today, remember with determining the order of a reaction, there's many ways you can do it. Okay, so one that we focused on a lot and you had your warm up on was from the lab data. Okay, that's what we did. Okay, today we are going to work on 2 and 3. Okay, so we're going to look at graphically how you can determine the order of a reaction, and as well we're going to look at nuclear decay, which is a type of first order reaction. Okay, and they're combined because we're both looking at them graphically. Okay, yesterday we also just went through if there's a single step reaction, you could just look at the coefficients, okay, if you're not given anything else. Okay, on Monday we will be looking at rate mechanism. Okay, that's when you're going to have multi-steps. You'll have a slow step, a fast step, but you'll have several steps that add up to one mechanism, and you're going to use these individual steps to figure out the order of the reaction. And then also yesterday, we talked about the unit of the rate constant. Okay, so remember you take the molarity, you negate it, you add 1, and then that gives you the reaction order. Okay, so today our focus is going to be graphically and half-life. Okay, so let's talk about what we're calling integrated rate laws. Okay, this is where we're going to take our reaction concentration and express it as a function of time. Okay, meaning what that means is we're going to take our graph, we're going to have time on the on the x-axis, and concentration of the reactant on the y-axis, and see what we get. Okay. Now, the form of the equation will depend on the order of the differential rate law. Okay, so how the equation comes out is going to depend on that differential rate law, which is what we talked about yesterday. Okay, and we'll review that. So we have 0 order, first order, and second order. These are the only orders we're going to work on. Okay, there are other orders that are possible. We're not looking at them. Okay, we're only working on 0, first, and second order. Okay, and each of these 3 orders will have their own integrated rate law. Okay, and all integrated rate laws will include time, which would be t, the rate constant, which we know as little k, final concentration, which we're going to call A sub t, or you could call it A sub f if you want to say final, and initial concentration, which would be A naught. Okay, so they'll all have those components in the equation. Okay, so let's first start with 0 order. Okay, so remember with 0 order, that means that the rate does not depend on the concentration. Okay, so if we start out, right, if this is our equation we're looking at, and A is our reactant, okay, remember the rate is depending on that reactant, okay, and if it's 0 order, that would mean the rate R would equal K times A to the 0 power, and we know that as 1. That's why rate equals K. Okay. Now, if you plot, okay, so here's our graph here. If you did a plot with some data, okay, for this differentiated rate, okay, and you plotted concentration versus time, it would give you a straight line with a negative slope. Okay, so it would give you a straight line with a negative slope. Okay, and the slope, actually, this should be a negative k here. The slope is a negative k. Oh, well, this is the absolute value. Now, our integrated, if you take some calculus, okay, and integrate our differentiated rate law, and if you'd like, let me know, and I'll show you how this is derived, this is your integrated rate law. Okay, so you have your concentration at some time t, negative k, which is the slope, and then your y-intercept, right? Remember, your y equals mx plus b. The slope is k, negative k, excuse me. The intercept is a naught, okay, and the y is a at some time t. All right, so let me just show you real quick how this equation came to be. Okay, so remember, for a zero order, we also know this. Okay, this is the definition of rate. Remember, it's the consumption of A, the change in A, over change in time. Okay, and we also know for a zero order, we also know that this equals K. Okay. Now, we can times both sides by delta T, okay, to get rid of it over here. Okay, and now we have negative delta okay. Now, instead of the negative here, what I'm going to do is get rid of it over here and put it over here. So now I have delta A equals negative K delta T. Okay, and I can also express delta A as A final, or let's call it A sub T, minus A naught, right? The change in A is going to be the A at some time t minus the initial A. Okay, and that's also going to equal negative K times T final, or TT, well, we'll just call it T final minus T initial. Okay, and if we assume T initial is 0, I can just get rid of that. And we'll just call TT. So we've got AT minus A naught equals negative KT. Okay, we're going to add A naught both sides. AT equals negative KT plus A naught. Okay, and there you get your final equation, which is your equation of the line. That's your integrated equation. Okay, and that's what's going to happen with all of them. Okay, number 2, I could show you too. Number 3, I would say Google it. Okay, so that is an equation. If we go back, this is the integrated equation that goes with the differentiated equation. Okay, and it makes a straight line with a negative k slope. Let's go into first order. Okay, I'm going to pause this so I can close my door. Okay, so this is first order rates. Okay, so remember, for first order, your rate is going to be your constant y. All right, this is going to be the best video ever. It's going to be like Watts family drama. All right, my 2 boys are fighting over the couch, and they're knocking each other off. Okay, so you got your differentiated equation. You got your rate equals your K times your A. Okay, remember, we're doing the whole thing with A turns to products. If it's first order, remember, the rate is going to equal K A to the first. Okay, that means first order. Okay, so that's how you get this first differentiated equation. The integrated one, okay, once you do your little calculus integrated, just like I showed you with the last one, this is going to be your integrated equation. Okay, so let me show you first, okay, when you graph, if you look at this first top graph, okay, so if you actually do the plot with the concentration of A over time, you can see that is not a straight line, right? You can see it's not a straight line, right? So the change in concentration has the same effect on rate as a zero order. It's just that instead, as the concentration doubles, the rate doubles. As the concentration doubles, the rate doubles. Okay, well, so then what you do, your goal is to make a straight line. You take the natural log of both sides and reorganize it, okay, where A naught is the initial concentration. AT, again, is a concentration at point T. The slope is actually K, the absolute value. You can actually graph the natural log of A and time, and you get a straight line. Okay, so you don't get a straight line like with the zero order, just using concentration as time. But if you take the natural log of A, you will get the straight line. Okay, so this is important because this information here is going to help us identify what order of reaction we have graphically. Okay, so let's go into the second order reaction rate. Okay, so remember we have our differentiated rate is K times A squared. Okay, I don't know why they're saying it's KB. Just know that for now. Okay, integrated looks like this. Okay, so this is the integrated equation. Okay, so this, if you plot concentration versus time, just concentration versus time, you get this curve. Okay, now if you plot the natural log, it still doesn't work, but if you plot 1 over concentration versus time, you get a slope with a positive K as the slope. Okay, and you actually get a positive slope here. You can see that here is your positive slope. Okay, so this is the integrated equation for a second order. Now, I also want to make sure you understand that these are all on your reference sheet, your chemistry, AP chemistry reference sheets. These integrated rate equations are on your reference sheet. Okay, and then, at the end, I can show you where if you need help finding it. Okay, and those are all on page 1 of the Canvas under reference materials. I believe it's the very first sheet you could print out. Okay, so here's a little summary sheet, okay, of what we just talked about, because I want you to look at the terminology on the left column as well as the information. Okay, so let's go through each one and make sure we understand what we're talking about. Okay, so this is what we've been doing. This is our rate laws here. Okay, we have zero order, we have first order, and we have second order. Okay, remember rate equals K. Rate equals K times concentration of A. Rate equals K times concentration of K squared. Okay, now I gotta fix my little formatting here for a minute, but let's look at the integrated rate law. Okay, integrated rate law. Okay, A equals negative KT plus A naught. Okay. You can see that you can get a straight line when you plot A on the y-axis versus T, and the K value is the absolute value of the slope. It looks something like this. Okay. Now, if you look at order 1, you know rate equals K times A. Here is your integrated equation. It's the same as the 0, except you have to take the natural log of the concentration. Okay, and when you plot to get a straight line, you do the natural log of A on the y-axis versus T. And the K value, again, is the absolute value of the slope. Okay, rate order 2. Okay, let me just adjust my little, actually, I'll just write it in. Actually, I think I just have to write in the lines. Give me 1 second. Just put these little lines in. It should just be like that. Okay, so the integrated rate law is 1 over concentration of A equals KT plus 1 over concentration of A naught. Okay, and your straight line plot will be 1 over A versus T, and your slope is, you don't need to take the absolute value, is going to be the K value. Okay, so this is a really, really good compilation of everything we just did. Okay, you do not have to know how to derive the integrated rate law. Okay, but I always like to know where things came from. I don't just like to know just it goes from rate law to integrated rate law. So I can do 0 and 1. I haven't really looked into how to do 0 and 2, but it's good enough for me. Okay, so we need to now take what we learned and be able to solve rate law problems. Okay? So take a minute. I'm going to pause the video. Just read this to yourself. I'll read it out loud in a minute. And we're going to take this one and use our information we just did and do this example out loud together. Okay, so we have the composition of ethanol. Okay, so here's our equation. We have ethanol decomposing into C2H5 in water. Okay, it tells us here that at 600 K, okay, that's one temperature, concentration versus time data were plotted and resulted in a straight line. Okay, so this is key information. If concentration versus time data were plotted, and it is a straight line with a negative slope, we know that this is a zero order reaction. Okay, so that's a hint right there. Okay, and it tells us the slope. Okay, so there's your slope. Determine the rate law, the integrated rate law, and the value of the rate constant. If initial concentration was 1.25 times 10 to the negative second, calculate the half-life of the reaction. How much time is required for all the ethanol to decompose? Okay, so let's take a look at this problem. Okay, so here is a plot, okay, showing you if we plotted concentration and time and our slope. Okay, now we determined that this has got to be a zero order reaction, okay, which means our slope remember our slope, the absolute value of the slope is going to be our K, okay, which is going to be 4 times 10 to the negative fifth moles per liter per second. Okay, so we just found out our K from the data. Okay. The second thing is to write, let me just make sure I got all the directions, but I believe the first thing they wanted was the rate law. Okay, so we know the rate law for a zero order reaction is going to be K. Okay, so remember it was rate equals K times a to the 0, which makes this 1. Okay, so our rate law is going to be 4.00 times 10 to the negative fifth mole per liter per second. And that's the answer to the first question. That's our rate law. Okay. Now the second thing they wanted was the integrated rate law. Okay, the integrated rate law. Okay, so let me take this again and copy it to another page. Okay. Do this. Okay, so we got that. Now, our integrated rate law for a zero order reaction looks like this. Okay, this is our integrated rate law. And this is the one I just showed you deriving, and it's also part of your table. It is also part of your equation sheet. Okay, so we have, I'm just writing it generically right now, A equals negative KT plus A naught. Now they give us some information. Okay, they gave us A naught. Okay, and now we have K. So our integrated rate law is going to be A equals negative 4.00 times 10 to the negative fifth mole per liter per second times T plus our A naught. This was given in the problem as 1.25 times 10 to the negative second. Okay, so what I just wrote out is our integrated rate law. Okay, so we have our rate law, our integrated rate law. Let's see what else it asked us to do. Okay, then it says calculate the half-life for the reaction. How much time is required for all the ethanol to decompose, excuse me. Okay, now for this, since we haven't really done half-life too much yet, okay, and I don't know if we're going to get to it today, I just know the general definition of half-life, which means it's the time it takes for half of the concentration to drop. Okay, so what I did was, just to figure out the half-life, I used, let me just erase this real quick. Okay, I just did it in a simple way. I knew that I wanted A to drop in half. Okay, so I wanted to see how much time it would take for this A to drop in half. Okay, so I took my initial amount, which was my 1.25 times 10 to the negative second. That's my A naught. And I divided it by 2. And I got 6.25 times 10 to the negative third. Okay, and then I just used that for my A. And then I solved for T. Okay, now there will be a half-life equation we're going to get into, but this is just an easier way to do it. So I had 6.25 times 10 to the negative 3 equals negative 4 times 10 to the negative 5t plus 1.25 times 10 to the negative second. And then I just solve for t, and I get a half-life of 156 seconds. Okay. And then I believe the last question just asked how long, let's see what it said, how long for all the methanol to, or ethanol, excuse me, to decompose. Okay, so that would mean your final, you're looking for T when A is 0. So you would do the same thing again. Okay. So the last part now, okay, instead of solving for, now that you, so you want your final, let me just erase this too. They're asking for it to all decompose, meaning you're looking for A to be 0. Okay, so you're going to solve again with A to be 0. Okay, so that would be when I get 312.5 seconds. Okay, so to figure out the times, okay, they wanted to know when it was all gone. So A was 0, and then I just solved for T using the integrated rate law. When I want to do the half-life, figure out the half-life, I just took A and divide the initial concentration by 2 to figure out the half-life. Okay, let's do one more problem. Okay, so this problem here tells you that the rate of reaction depends only on the concentration of H2O2. Constant temperature, the data was collected. Okay, so you can see that you have your time in your x-axis, okay, or excuse me, in the first column, okay, which would be your x-axis, right? And then you have two y's. Okay, when I put it in the calculator, I put it as L1 and L2. And if you're familiar with your calculator, that's where you would put your data. Okay, so you're going to determine the rate law, the integrated integrated rate law, and the value of the rate constant. Okay, so first of all, you got to figure out what order the reaction is. The way you're going to do that is you got to figure out where your straight line graph is. If the straight line is with the concentration of A over time, then it's a zero order, okay? If it's a straight line with the natural log of A over T, then it's a first order. Okay, they didn't give you data for the other one, so it's got to be one of the two. So remember when you do a linear regression, okay, the R squared's got to be as close to 1. Okay, does everybody know how to do a linear regression in your calculator? Okay, so when I put this in my calculator for the first column, I get an R squared value of 0.86. Okay, so that was for this when I did the regression. Okay, now I'm going to replot again. I'm going to hit Stat, Calc, go down to linear regression again. I'm going to pick the different list for Y as L3 for me. Hit Calculate, and I get my R squared value as 1. So my R squared, my regression is 1, which means the closest to 1 makes it a straight line. So that means this data makes a straight line, which is going to be first order. Okay, so this is my data. I know it's first order. Okay, so if I write the reaction, okay, for a first order, it's going to be R equals HK times H2O2 raised to the first power. Okay, for first order, the slope, remember, the absolute value of the slope is going to be my K. Okay, and for this, when I look at my slope, I get 8.33. And this is from my calculator, times 10 to the negative fourth. This is from my regression. Okay, so my rate law is going to be 8.33 times 10 to the negative fourth times the concentration of H2O2. Okay, and then for my integrated rate law, okay, I have the natural log of A equals negative KT plus the natural log of A naught. Okay. And when I plug in, I get the natural log of A equals negative 8.33 times 10 to the negative fourth T. And then I have here for my intercept 0. And that is your integrated rate law. Okay, so there's your rate law, your integrated rate law. And then the last thing they asked for was, okay, the rate constant, which we also determined, okay, which is the absolute value of the slope. That's been determined right here. And the last thing, calculate the concentration of hydrogen peroxide at 4,000 seconds after the start of the reaction. Okay, so after 4,000 seconds, you would take this equation here. Okay, so the natural log of A equals negative 8 8.33 times 10 to the negative fourth t. Okay, t they said was 4,000 seconds. So this could be 4,000. Okay, now we got to get a out of the natural log. Okay, so that would be take e to the, for both sides, you have to do e to the both sides. So that's going to be a equals second okay, e to the negative 8.33 times 10 to the negative fourth times 4,000. And I get concentration is 0.036. That's the concentration after 4,000 seconds. Okay. Now we are done with class. I'm going to pause this. I will upload the video and